Practice. So, exercises 7.4, 7.5, 7.6, good practice. And let me give you a slightly more challenging problem. So I'm going to define a recursive function f of n is equal to 1 if n equals 1. It's okay, now there are two cases, n even and n odd. Okay, so if n is even, it's going to equal f of n over 2 plus 1. So you can divide by 2 and then add 1. And if n is odd, f of n is f of n plus 1. So this is something that often happens in practice in computer science. You know, so some function, you halve it if n is even, so you halve it, for example, in binary search, or if n is odd, you pad it by 1, and now it becomes even, and then you'll halve it, okay? And so prove, a formula for f of n. Now you can tinker and figure out that formula, but in this case, I'm just going to tell you f of n is equal to 1 plus the ceiling of log base 2 of n. So it's complicated. So these functions that are like halving functions, they grow like the logarithm of n. Okay, so that's a challenge. If you'd like to take me up on that challenge, go for it. If you just want to see the solution, the proof by induction, it's in the text. Okay, let's talk about recurrences. So recurrences. Okay, so a recurrence is just a recursive function that's defined on the natural numbers. Okay, so we could say f of n, but we will typically say, f sub n. Okay, and I'll give you an example. Let's talk about the Fibonacci recurrence. Okay, this is a famous recurrence. It was developed by Fibonacci, as a somewhat approximate models of how rabbits reproduce. Okay, but it's been around, for longer. It's been seen in Sanskrit poetry, and there are lots of applications of the Fibonacci numbers today in practice. How spirals of flowers grow, and so on and so forth. So it's a very famous recurrence, and it's been studied a lot. Okay? And so I'll introduce you to not only the Fibonacci recurrence, but a notation that we use for recursive functions that are defined on the natural numbers, which we call recurrences. So the Fibonacci recurrence. Okay, so we typically write the terms in such a recurrence as f. So in this case, for the Fibonacci, f for Fibonacci 1, f2, f3, f4, and so on. Okay, let's do a few more. f5, f6. Okay. So now if this was a function, we could have said f of 1, f of 2, but because it's on the natural numbers, we list them as terms in a series or a sequence. Okay, and now the Fibonacci recurrence is as follows. So it says that f of fn is equal to fn minus 1 plus fn minus 2. Okay, now what this means is that in order to compute fn, I need to know fn minus 2. So I can compute, if I can compute f of n and f of n plus 1, then I can compute f of n plus 2. And the fact that, you need n minus 2 to compute n suggests that you need two base cases. So we typically, so the base cases are f1 equals 1, f2 equals 1. Okay, so this is an example of a recurrence. Okay, it gives you the nth term in the sequence in terms of, as a function of previous terms. And together with these base cases, it turns out that you can prove by induction all the terms are now well defined. And let's see how it goes. So f1 is 1. Okay, so this is 1, this is 1. Now, f1, f2. Okay, now f3. Okay, so f3 is f2 plus f1. So f2 plus f1, so 2. Okay, f4 is f3 plus f2. So 2 plus 3, 2 plus 1, 3. f5 is 3 plus 2, 5. f6 is 5 plus 3, 8. f7 is 8 plus 5, 13, and so on. Okay. So this is a very famous recursion, a famous recurrence, and we might ask interesting questions like, what is the nth term? Well, it turns out we can compute a closed form formula for the nth term, but instead, what we'll do is, for the moment, let's just bound the nth term. Okay, so we're analyzing this recursion. We sort of see how it's behaving. It's growing. It turns out it's growing very, very fast. Okay, and so claim And this is now to illustrate yet another, example with a recursion and how we can use induction to sort of analyze recursion. So I claim that, f sub n is at most 2 to the n. Okay. And we're going to use strong induction to prove this. Okay. And it turns out that, so let's analyze this claim. So base cases. And you'll see why I need 2 base cases, because I cannot apply the recursion, until n becomes larger than 2. Okay, larger than or equal to 3, because then I have, n f of 2 and f of 1. Okay, so I'm going to treat f of 1 and f of 2 separately. So this is for n greater equal to 1. So the base cases are, f of 1 equals 1, which is certainly less than 2 to the 1. 1 is less than 2, and f of 2 is equal to 1, which is certainly less than 2 raised to the power 2, which is 4. Okay? So true for f of 1 and f of 2. Okay. So this is a slight modification on strong induction, because typically in strong induction, you have 1 base case. But, just like in the recursion, we have 2 base cases, that translates into the induction and says, okay, we'll have 2 base cases in the induction. Okay, now, the induction step. So, if you think about what I have, I've proved the claim for n equals 1. Okay. I've proved the claim for n equals 2. Okay. Now, I would like to know whether it holds for n equals 3, n equals 4, and so on. Okay. Now, in the strong induction hypothesis, if I'm trying to prove, if I can show that if the claim holds for 1 and 2, it implies 3, then I can, and I have 1 and 2, then I can infer 3. And then if I show that if it holds for 1, 2, and 3, then it implies 4. That's the strong induction method. If I can assume that it's true for all these and conclude that it's true for 4, then I'll be able to infer 4, and so on. Okay, so the induction step. In the induction step, I'm going to now try to prove that for all n greater than or equal to 2, prove for all n greater than or equal to 2, so I'm going to prove that P1 and P2 and Pn. Okay, so if I assume it for all the values up to n, then that's going to imply it for Pn plus 1. So that's the strong induction step. Okay. So let's see how that's going to work in this case. Well, okay, so let's consider n greater equal to 2. Okay, so and we get to assume this. So we get to assume that Fn is less than 2 to the n for n equals 1, 2, up to n. And now we need to prove Pn plus 1. We need to prove, so assume, this is what we get to assume to prove that implication, and we need to prove Fn plus 1 less than 2 to the n plus 1. Okay, that's what we need to prove. But we do know that Fn plus 1 is equal to Fn plus Fn minus 1. It's this value minus 1, this value plus minus 2. Okay, Fn plus 1 minus 1, Fn plus 1 minus 2. But this is less equal to 2 to the n. And this is less equal to 2 to the n minus 1. And that's the induction hypothesis. The induction hypothesis said all the Fibonacci numbers are less than their corresponding, than 2 raised to their corresponding n. That we got to assume. Okay. Well, this is less than 2 to the n plus 2 to the n. Yeah, and 2 to the n plus 2 to the n is equal to 2 to the n plus 1. So there, I've proved it. End of proof. So by induction, we're done. By induction, Fn is less than 2 to the n for all n greater than or equal to 1. Okay. N equals 1 and 2 came from the base cases, and the rest follow from the the strong induction methodology. Okay, so the Fibonacci numbers, example of a recurrence. We can analyze the Fibonacci numbers. In particular, we showed that the Fibonacci numbers are at most growing like 2 to the power n. Okay. Do they indeed grow very fast? Yes. So exercise. So, continuing with this exercise. So let's call this, exercise 1. This is 2, 3. Show, prove the Fibonacci number Fn is greater than or equal to is greater than 3/2 to the power n, for some n large enough. And let me tell you what that n large enough is. For n greater equal to 11. Okay. So it's clearly not true for n equals 1 because f1 is 1 and this is 3/2. f2 is 1 and this is 3/2 squared, which is 2.25. And so, but eventually this Fibonacci number gets bigger than 3/2 to the n, and 3/2 is this is 1.5 to the n. And so this means that the Fibonacci number is growing at least exponentially. So it grows at least as large, as quickly as 1.5 to the n, and at most as quickly as 2 to the n. Okay, so exercises in induction and recursion. Let's do another example. Application of recursion / induction.